This lesson is about even and odd functions, which is just another way to classify functions. The way we've classified functions so far is basically by their shapes, which depends on if they're linear or exponential, quadratic, absolute value, or etc. Basically, the operations we see determine what the shape is. Another way we classify functions is by their symmetries, and there's two specific types of symmetry that we create classifications for. The terms even and odd function come from the symmetry of power functions that have an even exponent or an odd exponent respectively. So as a review of what we did in Unit 3, was actually the first lesson, we are going to look at what those power functions look like. So power functions, just to make sure we remember what we're talking about, power function is something like this, where it's one term. We have a number in the front, we have x, and we have some sort of power b. So the different situations we have are if b is even, so like this one we have an even exponent, and the number in front is positive. So for example, this one, the graph will go through the origin as all power functions do, and both ends will go up. On the next one, it says b is even and a is negative. So we still have the arrows going in the same direction because b is even, and with a negative, basically, now that we know about our transformation rules, that's like negative f of x, right? If I made this negative 5x squared, so that's a reflection in the x-axis, and the graph goes this way. So we didn't think about it with transformations in Unit 3, but that's basically what it is. So the type of symmetry that both of these graphs have is that they're symmetric or have line symmetry specifically over the y-axis. So if I reflected those graphs over the y-axis, basically this side would come over here, and the negative side would go to the positive side. It would be the same graph. So in function notation, what we're saying is the original graph is equal to the graph reflected over the y-axis. And our function notation for reflecting over the y-axis is f of negative x. So this is the algebraic definition. We'll come back to that at the end of the lesson. But basically for now, even functions have line symmetry over the y-axis, or they're symmetric over the y-axis. Now, even power functions are a special type of even function. They're what gives even functions their name, but there are other types of functions that have this symmetry, and they're also considered even functions. Moving down to the odd functions, so that could be something like this, where we'll do a positive one first. So let's say for the even or oddness of a, right? If a is even or odd, doesn't make a difference in the shape. Basically, it's the exponent, so we're saying b, the exponent, is odd, so we'll do 4x cubed, and a is positive. So that graph is going to go like this, and if I threw a negative sign on there, right, that would reflect it over the x-axis again, and the graph would go like this. So these graphs, if we folded them over the y-axis, they would not be the same. They have a different type of symmetry. And basically, that's rotational symmetry of 180. About the origin. So the origin is the center of that rotation. Okay. And an interesting fact is when we rotate things 180 degrees about the origin, it actually has the same effect of reflecting in the x-axis or the and the y-axis. So both of those two. So if you can imagine, if I was going to reflect that graph over the x-axis, right, it would come down here. And if I then also went over the y-axis, right, it would go back onto itself, which is that symmetry. So that's important to know, because when we talk about our function rule that shows, or the function rule that will say something's an odd function, we're saying the function is equal to the function after a reflection in the x-axis and the y-axis. So negative f of negative x. And as I said, we'll come back to these algebraic definitions later. For now, we can just know that odd functions have rotational symmetry of 180 degrees about the origin. I like to think of it this way. You can also say it's symmetric about the origin, but saying the rotational symmetry kind of helps me think about it better. On this page, we have a summary of those definitions. We have the graphical way of looking at things, looking for their symmetry, and then we also have the function notation rules that we had on the other page. On this page, we're going to focus on the graphs, and we're going to look to see if graphs on this page have either of those types of symmetries. So this first one, I can tell is an absolute value function based on the shape. And at first, I always look for even. I think it's a little easier, and this graph is symmetric over the y-axis. It has line symmetry over the y-axis, so it's an even function. There is only one function that's both, but just to see what we're looking for, if this function was odd, if I rotated it 180 around the origin, I'd end up with the graph down here. It definitely doesn't go onto itself, so it's not an odd function. I'm going to erase that just so it's not confusing to look back at. The next one does have line symmetry, but it's not line symmetry over the y-axis. It looks like it's line symmetry over the line x equals 1. So we're going to rate, first off, we'll check. I can tell that when I rotate it 180, it would end up, somewhere down here. So it definitely is not odd. Looks maybe closer to being even if that's a thing, but this one is neither. And a lot of graphs are. A lot of graphs don't have either of these symmetries. The next one is not even, not symmetric over the y-axis. If I rotate it 180, those two, the arrow, the part that's pointing up and the part that's pointing down will switch, but it's not rotational symmetry about the origin because this graph looks like a cubic or something, a x to the fifth graph that was moved up 3. So it doesn't have that. So this is also neither. Moving down the page, this one, and hopefully you can start to see, it's not even, right? If I flip it over the y-axis, it's not going to be the same. But since we're just looking at a graph, if it looks reasonable, we're going to assume that's true. These two bumps, right, this bump and that bump, if I rotated it 180, those would land on each other. And it looks worse once I trace it, but if I go back, I can see, and I'm pretty reasonably sure that this is an odd graph. This has rotational symmetry of 180 about the origin. The next one, and you should at some point start to just classify the remaining ones. This one does have line symmetry over the y-axis, so this is even. Does not have rotational symmetry of 180. We can see those arrows would point down if I rotated it, both of them. The next graph basically does not have the line symmetry, but if I rotated it 180, I can see that it would fall back on itself, and specifically about the origin, it would fall back on itself, so this one's odd. And our last three are graphs that will, or at least the last two or the next two, I guess, not the last two. G and H are ones that we will do later in the year. This one does have that line symmetry if I reflect over the y-axis, so this is even. And this one has all those points that goes through the origin. They're going in the opposite directions. They come back. So this one, if you can picture, if I can rotate it 180 about the origin, it would be the same. This one's odd. So here is our line, specifically y equals 0. And this one is even, right? Because if I fold it over the y-axis, it's going to be the same. But if I rotate it 180, it would also land on itself. And this is the only function that's both even and odd. Okay, it's not a very interesting function. It's just a straight line, straight horizontal line through the origin, but it has both qualities.